I would like to evaluate the limit as x approaches 3 for 3 functions which look a little bit similar and see how they behave. The first example is x squared minus 9 over x minus 3. The second example is x minus 3 modulus over x minus 3. The third example is 1 over x minus 3 cubed. You would notice that all 3 functions have x minus 3 as the denominator. So let's see what happens when we have x minus 3 as the denominator, but the numerator, x squared minus 9, the absolute value of x minus 3 and 1. So let's see what happens when the numerator is different, but the denominator is the same. Another thing to notice is that there will be some sort of asymptote at x minus 3 equals 0. X minus 3 equals 0 implies x equals 3. We know that x minus 3 cannot be 0, therefore x cannot be equal to 3 because we cannot divide by 0. Let's see what happens to these 3 functions. The first function is x squared minus 9 over x minus 3. We can factorize x squared minus 9 as x plus 3, x minus 3, and you notice that the x minus 3 cancels out. So you get a function that looks like this. If you draw it on the graph, it looks like this. It passes through 3, and there's a point with the value x equals 3 and y equals 6 right here. You can drop this down, drop this across. The slope is 1. It's shifted up by 3 at every single point. looking at the function, let's see what happens as we approach 3. As x squared minus 9 over x minus 3. For this graph, as x approaches 3 from below, we have the function f of, from below would be, I'll pick an example, f of 2.99, f of 2.99 equals, I can write it as this, in this format, so it's easier to calculate. 2.99 plus 3 times 2.99 minus 3 over, same here, 2.99 minus 3. So again, to make the calculation simple, we can just cancel out these two terms, and the value would be 2.99 plus 3, which would be almost 6. It will be 5.99. That's the first evaluation. The second evaluation is as x approaches 3 from the positive. That means it comes in for this, as x approaches 3 from the negative, we're coming in from this side. For x approaches 3 from the positive, we are coming in from this side. So we can say f of 3.01. That's equal to 3.01 plus 3, 3.01 minus 3 over 3.01 minus 3. This cancels out, and the answer is 3.01 plus 3, which is 6.01. So we can say that the limit as x approaches 3 for this function, x squared minus 9 over x minus 3, approaches 6 or equals 6. But there's a but here. F of 3 is not defined, is undefined. Because of the way we have written this function, even though the function x plus 3 is okay, but if we write it as in this format, x squared minus 9 over x minus 3, it implies that at x equals 3, there is no, it's 0, and therefore there's no definition. So rightly speaking, at the point 36, there is an asymptote. And rightly speaking, I should be writing a circle around it. So it should look like this. A circle. I'll put it in black so it's a bit more visible. So it approaches but does not get to but does not touch the value 3, 6. This is the first example, x squared minus 9 over x minus 3. The second example is as follows. F of x equals absolute value of x minus 3 divide by x minus 3. This looks interesting. So what's happening? Let's take a look at what happened, how it behaves. As x approaches 3 from below, what happens? It implies that, let's take a value 2.99 again. F of 2.99 equals the absolute value of 2.99 minus 3 over 2.99 minus 3. 2.99 minus 3 is minus 0.01. We take the absolute value of that over 0.01 but negative. The absolute value of this is positive, so it's positive 0.01 over negative 0.01, which gives us negative 1. As x approaches 3, it cannot get to 3, that would be undefined, but as it approaches 3 from the positive, f of 3.01, a little bit bigger than 3, coming in from the positive, that's equal to 3.01 minus 3. Take the absolute value of that over 3.01 minus 3. So this would be 0.01 absolute over 0.01, which is 0.01 over 0.01, which is plus 1. So we have minus 1 and plus 1. Looks interesting. Let's see how it behaves. I'm going to draw the graph here. So something happens at the point x equals 3. So 1, 2, 3. Plus 3. So when x is approaching 3 from below, that means we're going from towards this direction. X approaches minus 1. This would be minus 1. Minus 1 is right here. So it approaches minus 1, but it never gets to minus 1. Plus 1. As x comes in from above, that means x approaches plus 3 from above, the function approaches plus 1. but never touches plus 1. So this is how the function is drawn, and this function is x minus 3, the absolute modulus of x minus 3 over x minus 3. This is x. If it touches, we can either draw it like this, xy, or we can draw it like this with a bold dot. If it doesn't touch, we draw it with a empty dot as above. This is how the second function looks like. Remember what I said below before, x minus 3 equals 0 because the denominator cannot be equal to 0, which implies x equals 3 is undefined, or D and E does not exist. This point does not exist. It approaches this point, but it never touches this point. You can put as many zeros as you want here and here, but you still get the answer to be minus 1. You can put as many zeros as you want in the numerator and denominator, but you still get plus 1, approaches plus 1. The last equation is 1 over x minus 3 cubed. So as x approaches 3 from below, what do we get? We get f of 2.99. This is a number which is a little bit below 3. Then it will be equal to 1 over 2.99 minus 3 cubed, which is equal to 1 over 0.01 minus 0.01 cubed, which is equal to, there are 2 decimal places, so there's 6, so we have to go back 6. 1, 2, 3, 4, 5, 6, and it's cubed, so the minus remains, so 1 over this number, and this is equal to minus 1 million. The way to look at this is to say to yourself, if I'm going to bring this point right up to the front, how many zeros do I have to add? Well, I have to add 1, 2, 3, 4, 5, 6. So to bring this decimal right up to the front, so where it becomes 1, you have to add 6 zeros, not 5 zeros. You have to add 6 zeros. The other approach is x approaches 3 from above, coming in this way. Then we have the function 3.01, that's equal to 1 over 3.01 minus 3 cubed equals 1 over 0.01 cubed. It's the same value except there's no 0, so just plus 1 million. let's draw the function. Let's see how it looks like. It's x, and this is 1 over x minus 3 cubed. There will be an asymptote at 3. As x approaches 3 from the negative, the y value is a very big negative number, so it is as x approaches plus 3 from the negative, meaning it's coming in this way, the value of y gets bigger and bigger, like this. And as x approaches 3 from this direction, from the positive direction, y gets bigger and bigger, so it will get bigger and bigger this way. So the function actually looks like this. And there is an asymptote at x equals 3. Right here. This is the asymptote. And the function crosses the y value at y equals 0, means 1 over x minus 3 cubed equals 0. There is another asymptote as at y equals 0, because you cannot have a 0 here too, as y approaches negative infinity, as x approaches negative infinity, y also approaches negative infinity. The reason is, if you write the equation y equals 1 over x minus 3 cubed, if x is a very large number, let's just call it delta, so 1 over delta minus 3 cubed, as x is a very large negative number, you have this minus 3 actually becomes insignificant. So you have a very large negative number cubed. So that's still equal to a very large negative number. And so this would be a very small negative number. Approaches 0. Excuse me. Approaches 0 from below. I made a mistake here. Why would approach 0 from below? Because 1 over a large negative number is approaching 0 from below. We can confirm this by making a graph with our calculator right here. The function is 1 over x minus 3 cubed. 1 over x minus 3 to the power of 3. So we can see from here we have an asymptote between 2 and 4, which is 3, which this is the asymptote. And then we can see that it approaches 0 at the value at the x-axis. That means at the value y equals 0. So to summarize, what we have done is we have taken the 3 functions and show you in each case what happens, how the function behaves, even though the denominator is the same, x minus 3. This is nearly the same, x minus 3 cubed. It just means that when the denominator is 0, we have an asymptote. So this is the first equation, x squared minus 9 over x minus 3. It reduces to a straight line, so we can draw it a straight line, but because of the way we have defined it, we cannot. If this was x plus 3, the line would pass right through the point 3, x equals 3, y equals 6. But because of the way we have defined it as x squared minus 9 over x minus 3, because of the way we define it, then this function has no value at the point x equals 3. So we have to exclude this point from the line. This is the second equation, the modulus. Here we have to, from our calculation, we can see, from our analysis, not calculation, analysis, we can see that minus 1 and plus 1 are points that we approach, but we cannot touch. So minus 1 here and plus 1 here. The reason why we cannot touch the points is because x cannot be equal to 3. Because if x equals 3, we are dividing by 0, which is an undefined value. X minus 3 equals 0 is undefined or does not exist, D and E. So we draw a line from here to here and from here to here, but we exclude the point 3, 1 and 3, minus 1. If you want to include a point, you draw it with a filled-in dot. And if you want to exclude a point, you draw it in with an empty dot. And the last equation we looked at was 1 over x minus 3 cubed. And so we get a function that looks like this. You can reconfirm it one more time with your calculator. It would look like this. It's okay to use your calculator to confirm your analysis after you've done the analysis. Don't do it before, because then you wouldn't be able to do the analysis properly. You because you would already know the answer. It's better to work it out and then have a look to confirm your answer. And what we got is an asymptote, same thing as the other two. The value at x minus 3 cannot exist, but instead of having a dot like this or like this, what we have is an asymptote where the value goes nearer and nearer but does not touch. Thank you for listening. Talk to you and see you next lesson. Bye.